I guess now it's recording. Good morning on this rainy day. I hope the screen is not too dark for you. We're gonna continue with where we left last time. Okay. So last time we were taking the limit of xn and turned out to be the limit of this, and this is less or equal to x0. This is, we notice that this is an exponential function, and the -1 comes from, because you're going to make a substitution, say I equal j plus 1, and then I equal to 1 instead of 0. So that's why the -1 comes from. But this is what's important, that this value is finite because k is finite, h is finite. So this value is finite, so this series converge. Okay, so hence by the Weierstrass M test, xn converges uniformly, say, to a function x of t. Okay, next we show x of t is a solution of 2.11 on D. Remember, that is 2.11. Okay, so to do so, we're gonna take a look at, so let's take a look at xt minus x0. That is xt minus x0 minus xn plus xn, and they all have t in them. And that is xt minus xn of t plus, or may I say, less or equal to, plus xn minus x0. Okay, now we know what's xn minus 0, so this is less or equal to x of t minus xn of t, plus what is xn of t minus x0? We did compute this from here sometimes before. Okay, so this is m times t minus t naught. Okay, remember what xn is. Xn of t was x0 plus t0 to t f of s xs ds. So if you look at xn minus x0 is less or equal to, this is m, and then the integral from t0 to t ds. So this is m t minus t naught, and this is what this value is coming from. Okay. If you take the limit as n goes to infinity, we're gonna get xt minus x0 is equal to the limit as n goes to infinity, xt minus xn of t plus m t minus t naught. Okay. Now, so xn minus x, remember xn converges to, say, to a function x. So this value is 0 plus m t minus t naught. Okay. And this is less or equal to m h. Why? Because t minus t naught less or equal to h. Because on D, t minus t naught is less or equal to h. And that is less than b, because the way h was defined. All right. So we showed x of t belong to d. Remember, this is the limit. This is the limit of the sequence. Next, we show that x satisfies the differential equation. All right. All right. Now, since xn of t converges uniformly and xn of t is continuous for every n, and since f of t, x of t is continuous, we have that the limit as n goes to infinity, t naught to t, f of s x n of s ds is equal to t naught to t, the limit as n goes to infinity, f of s xn of s ds. Okay? So because f is continuous, all right? So consequently, we have x of t. Remember, this is the limit as n goes to infinity, xn of t. Is that right? But what is xn of t? Well, I mean, I really don't xn of t, but what is that? That is x0 plus t0 to t, the limit as n goes to infinity, f of s, x minus 1 of s ds, and that is x naught plus t naught to t of f of s, the limit as n goes to infinity of x minus 1 of s ds, and that is x naught plus t naught to t f of s x of s ds. Okay? Because this limit is xs. So guess what? That is a solution, which is a solution of 2.1.1. Go back at the beginning of the proof how we wrote the solution as an integral equation. All right? So that really finished the theorem. That proves the theorem. Now, I'm going to do some kind of application. Okay? Are you guys, were you guys able to open the videos yesterday? If any did, please reply in a chat or something. All right, so you were able to go to the link that I shared with you, right? And get to it. Okay. All right, so now let us show something different we're gonna do two examples that are related to this theorem. Okay. Next, we go over two examples that are related to the proven theorem, to the theorem that we just proved. Okay. All right. The first is and that is example 2.2. So let's take a look at x prime of t, that is 2t, 1 plus x, with x of 0 equals 0. Why don't you go ahead, guys, and find the exact solution? So I'm going to ask you, find the exact solution. Just use separation of variables. So go ahead and do it. I'll give you a couple minutes, then I will continue. All right, I can help you out with that. So this is dx over dt equal 2t 1 plus x, or dx over 1 plus x equal 2t, which means ln of 1 plus x of t equal t squared plus c. Take exponential, you get 1 plus x of t equal k times e to the t squared, or x of t equal k e to the t squared minus 1. Now 0 is x of 0, that is k minus 1, that implies k equal 1. So the exact solution is x of t equal to e to the t squared minus 1. Okay? Now, so you got that, right? Now, we use the sequence formula in the theorem to find xn of t for n bigger or equal to 0? Well, recall xn of t was x0 plus t0 to t f of s x of s ds. Okay, so here x0 is 0, t0 is 0, and f of t x of t is 2t times 1 plus x. So these, what we have. Okay? All right. So let's start computing. Well, for n equal 1, we get, oh, sorry guys, this is xn minus 1 here, not xs, n minus 1. For n equal 1, we get x1 is 0 plus 0 to t f of s x0 of s ds. Do you see what happened? Because this is xn minus 1. Okay? Not x. This is in the formula. All right. So what is f of s x0 from here? That is 2s times 1 plus x0. That is 2s times 1 plus 0. That is 2s. And so this is 0 to t, 2s ds, which is s squared from 0 to t, which is t squared. There we go. We got x1 now. It's t squared. Any questions? What about x1? For n equal to 2, I got x2 equals 0 to t. Again, this is 0. And I'm going to have f of s x1 of s ds. So what is x1 of s? x1 of s is s squared from here. So f of s x1 of s is 2s times 1 plus x1 of s. That is 2s times 1 plus s squared. Okay? And so this is 0 to t, 2s times 1 plus s squared ds. And that is 0 to t, 2s plus 2s cubed ds. And that is s squared plus 2/3 plus 2/4 s4 from 0 to t, and that is s squared, sorry, that is t squared plus t4 over 2. So that is x2. All right? if we continue this process, we arrive at xn of t equal to t squared plus t4 over 2 plus t6 over 3 okay, and plus t6 over 3 factorial, and that is going to be in terms of summation n equals 0 to n of t squared to power I over I factorial minus 1. Oh, I equals 0. Okay. All right. The hell? I swear to God, I disabled the waiting room. I don't know what's going on. I don't know. I will try again. All right. So this is, so we know we have the exact solution and we have the sequence of solution. So we're gonna show that xn of t converges to x of t uniform. That's what we need to show. That this xn as t goes to infinity, sorry, as n goes to infinity is x of t. So as n goes to infinity, this is what we need to show. All right, I'm gonna flip the board. All right. So let's flip the board. Oh, I already flipped it. All right. So we have a definition before we continue. Okay. A sequence xn of t. All right. X of t, a sequence xn of t of functions in C A B R converges uniformly to X in the same thing, C A B R, if the limit as n goes to infinity of the norm xn of t minus x is equal to 0. Okay? All right. So we have the exact solution on 0, 1. Let's take particular interval. Bounded interval is x of t equal e to the t square minus 1. And xn of t is I equals 0 to n t squared to power I over I factorial minus 1. So let's use the maximum norm. Let's use the maximum norm. So we're going to take a look at the limit as n goes to infinity of xn of t minus x is the limit as n goes to infinity of the maximum of t in 0, 1. Okay? Of I equals 0 to n t squared to power I over I factorial minus 1 minus e to the t squared minus 1. Now, this minus 1 cancel out. And so what we're going to have is the limit as n goes to infinity of I equals 0 to n t squared to power I over I factorial minus I equals 0 to infinity of t squared to power I over I factorial. Where did this come from? This one has a power series, this one. You see what happened? And I have the maximum. So this is the limit as n goes to infinity of the maximum t in 0, 1 of, if I add these together, I get I equal n plus 1 to infinity of t squared to power I over I factorial. But the maximum for that is at 1, the maximum. So I'm going to drop the maximum. This is the limit as n goes to infinity of I equal n plus 1 to infinity of 1 over 1 I factorial, and that is 0. Okay? Because you subtract the 2 and you get this. Okay? And then remember, you have the absolute value. You have the absolute value. Okay? And then you have the absolute value, and then you put t squared and you get 0. So by this one, then xn of t converges to x of t uniform. Since 0, 1 is arbitrary, we can extend it to the whole real line, the whole real line, positive line. For example, take 0, 100, 0, 200, whatever, and you still get the same result. Okay? So here is an example in which we found the exact solution and then found the iteration, the sequence of solution, and we showed under the maximum norm, the sequence of solution converged to the exact solution. Okay? All right, any questions?
You chose to use the maximum norm. Could we use any norm here?
Well, the maximum norm is the easiest because you have a bounded interval, so always use the maximum norm.
Gotcha.
If this was open, you use the supremum norm, but you'll end up with the same condition, right? With the same result. Okay? So, because remember, the supremum of an open interval of a function that is continuous does not exist. Supremum. The maximum does not exist. For example, if you have f of x equal to x squared on 0, 1, right? So the function is increasing, but here there is a hole at 1. So the max does not exist, but the supreme of f of x is 1. It does exist. Okay? So we're going to take the maximum here.
Makes sense. Thank you.
Mm-hmm. All right, any other questions? So think about it, and now we're going to do a direct application to the theorem. All right, here's another example. Use theorem 2.12 to find the interval of existence. So, by the way, for those who are reading the textbook, what do you think of the book? Is it any different from the other books that I've written? What do you think of it? I think the theoretical standard is a little bit deeper here. So just give me your opinion if you've been reading through the book. What do you think? Because I may be able to do a second edition on it in a year or so. All right, so we're gonna have x prime of t equal 1 plus x squared, and x of 0 is 1. Remember, this is t0. Okay? So we're gonna take d to be tx, and this is x0. T minus t0 less or equal to a, and x minus x0 less or equal to b, and this is the same as tx, t less or equal to a, and x minus 1 less or equal to b. So we're gonna find this b. Okay, so what is our function? Our function f of tx is 1 plus x squared, which is increasing, correct? Which is increasing function. All right, so what do we know? We know that x minus 1 less or equal to b, that means minus b less or equal to x minus 1 less or equal to b, add 1 minus b less or equal to x less or equal to b plus 1. So the maximum of f of tx on a t between 0 and a, let's keep t, so the maximum for that on d, so this is the maximum on d. Remember, for t, x belong to d, is, well, this is an increasing function, and the highest, and the interval is b plus 1, so this is 1 plus b plus 1 squared. Okay? So this is the maximum, and remember, this is our number m in the theorem. So m is this one. So now, so h is minimum of a and b over m. Well, let's keep a fixed, whatever. So what is, so this is minimum of a and b over 1 plus b plus 1 squared. Okay? Okay, so basically you need to find the maximum of that. So we want to find, so let g of b equal b over 1 plus b plus 1 squared. So we need to maximize g of b. Because the minimum of these two biggest numbers, you don't take the smallest, you'll be in trouble. So you need to take the biggest interval. Remember what we are doing. So you're talking the minimum of the two biggest numbers. So if you say we need the minimum, then you are in trouble. All right. So I'm gonna flip the board if you are with me, and I'm gonna, because I missed some work in the book. I skipped, not I missed. Okay. Any questions so far? I know for those of you who had me in the past, realize that this is really a different beast, you know, of a class. Again, this is a theoretical class. So let me move over here. So we have g of b is b over 1 plus b plus 1 squared. Well, to maximize a function, we need to look at the derivative. So g prime of b is 1 times 1 plus b plus 1 squared minus b times 2 times b plus 1 over 1 plus b plus 1 square. Okay? And this is 1. I'm going to expand this one. B squared plus 2b plus 1 minus b times 2b plus 2 over 1 plus b plus 1 squared. Okay? So this is equal to 1 plus 1 is 2. B squared minus 2b squared is minus b squared. Minus 2b plus 2b go away. Over 1 plus b plus 1 squared. So g prime of b, we need to find the critical point if and only if 2 minus b squared equals 0, if and only if b equal plus or minus square root of 2. So since b is positive, we take b to be the square root of 2. Okay? Now, how would I know the function g is maximized at b equals square root of 2? I mean, I can wave my hand and I say, heck, g is maximized at the square root of 2. But what do you remember from Calc 1? What else do you need to check to make sure b equals square root of 2 give you a maximum, not a minimum? Anybody?
Second derivative.
So we're going to have to take the second derivative and show it is negative or positive. Negative, right? Okay? All right. Okay, so I can erase this. So now this is my g prime. So if I take g second of b, that is minus 2b times 1 plus b plus 1 squared is squared minus 2 minus b squared times oh no, minus 2 minus b squared. Now I need to take the derivative of that. That will be 2 times 1 plus b plus 1 squared times 2 times b plus 1. There. You're going to get 2 times 1 plus b plus 1 to power 1 times the derivative on the inside, which is 2 times b plus 1 over 1 plus b plus 1 squared to power 4. Okay, I can simplify minus 2b minus 2 minus b squared, and I'm going to have 2, this will go away, this will go away, times 2 times b plus 1 over 1 plus b plus 1 squared cubed. I factor this term out. It's in both places. Okay? And then so what is this equal to? This is, well, you can see this is minus 2. Let's put b equals square root of 2. So let's substitute b equals square root of 2. So g second of square root of 2 is minus 2 square root of 2. This will be 0 minus 0 over 1 plus square root of 2 plus 1 square cube. That is less than 0. Okay? Because this will cancel out. This will be 2 minus 2. Will cancel out, so the whole thing will drop out. You get minus 2 square root of 2 over something positive. So indeed, g of b is maximized at b equals square root of 2. Okay? So we need to find now g over square root of 2. So the max g of square root of 2 over square root of 2 over 1 plus square root of 2 plus 1 squared. So remember, the interval is, right? So h, what is h? It is minimum of a and g of b, correct? So that is the minimum of a and the square root of 2 over 1 plus square root of 2 plus 1 squared. And then our interval of existence that is given by the theorem is t minus t naught less or equal to h, or t less or equal to h, or t less or equal to the square root of 2 over 1 plus the square root of 2 plus 1 squared. Okay? Because this value, you will see, why aren't you taking A? Well, it's no guarantee that the maximum of that is within A. So I take this one and we will see that A is always within this interval. So in other words, minus square root of 2 over 1 plus square root of 2 plus 1 square is less or equal to t is less or equal to square root of 2 over 1 plus 1 square. So this is the interval of existence. All right? Now, you see, you can find, like the previous example, you can find actually, I don't know if you can solve this one, but this, we will have something that said that the solution exists for all time. So this is like a local existence because this only gives us a small interval. But you can extend this later on. We have more theorem that to extend this and that show the theorem if there is a certain function on f that the solution exists for all time. So for this one now, so let's say I take now b equal, let's say a is 10. Correct? Then what do I have? I have t less or equal to 10. So minus 10 less or equal to t less or equal to 10. Correct? So that interval, so which is, so this interval exists in that one. So this is what I will say. So our obtained interval, which is this one, lies inside minus 10 less or equal to t less or equal to 10. Okay? And whatever a you take, as long as b is bigger than a, this is correct. Because b has to be bigger than a. Okay? Because they are ordered that way. For example, if you take a equal to 10, you may take b equal to 10.1. Then this will always be bigger than that. So this will contain in this all the time. All right, any questions? So our obtained interval, I mean, is this one. This is our obtained interval. This lies inside minus 10 less or equal to t less or equal to 10. So you got the idea? All right. So enough of this theorem. Now you should be able to do all your homework. I mean, actually, and more. I'm going to assign homework tomorrow. And I was excited today that I found out that on Monday we don't have a classes. Heck with it. Those meeting every day for almost an hour and a half is killing me. It's a little bit rough on my back, but that's all right. Okay. Any questions? So you saw how we did this application. All right. Everything is falling apart here. So there is a corollary. This is corollary 2.1. Let D be a subset of R cross R, and F is a subset of C of D into R, and del F, the partial with respect to X, is continuous on D. Okay? Then for any T naught, X naught belong to D, the IVP, initial value problem 2.1, has a unique solution on an interval containing T naught in its domain. Okay? So this is a very powerful and a corollary. So basically, all you need to look as if F is continuous, specify your D, and the partial derivative of F with respect to X is continuous. And then you can find a set D where the function is. Oh, by the way, in the theorem, we have not showed uniqueness yet. I will show uniqueness after I prove another lemma. Okay? All right. Questions? Okay, so here's an example. X prime of t is equal to t times x to the 1/2. Okay? So f is continuous on the set. I don't know if I'm talking about the real number, so this is continuous on R across 0 to infinity. This is t, and this is for x. Why? Because we want x to be positive, bigger or equal to 0. What about f of tx? F of tx is tx to the 1/2. Del f over del x is 1/2 t times x to the minus 1/2, and this is t over 2 square root of x. So I take this back, and del f over del x is continuous on R cross 0 to infinity. So our set D is all the x where t is in R, where minus infinity less than t less than infinity, and x is a positive. Okay? So you see what happened here? So what do we conclude? Hence, for any t naught x naught in D, the equation, the initial value problem, has a unique solution. So for example, can I take x prime of t is t x to the 1/2 and x of 0 equal -1. Can I do that? The answer is no, of course. Because remember, this is x naught. And x naught has to be in D and T naught, sorry. And D required x naught, so this is no. What about x of 0 equal 1? That is good. So as long as we excluding the upper half plane, as long as your solution are here or here or here, you have a unique solution. You're gonna avoid x not equal 0. Okay? All right. So that is done. Now I'm gonna do a huge skip because I really don't have time. This book was written as a 2-semester class, and I don't have much time to really do everything I need to, because I wanna go to stability and Lyapunov functions and so forth. If I do that, I have to sacrifice a lot of earlier material, especially in chapter 2. But if you're interested, it is a very sophisticated, deep, abstract material. I would not recommend you read it. Just follow my lectures, what I do for now, because I want to spend more time on stability, Lyapunov functions, how to construct them, because these are very important topics for research and for application to engineering, to stability of systems and other things. All right. And Lyapunov function is still a wide open research area. And if you go to Google citation or Google search on my publication, you will find about 170. And I would say about 30 to 45% of my paper's titles include the word Lyapunov functions. Okay? So I made a living out of it. Anyway. Okay. So now I'm gonna go all the way to page 39. Okay, let me throw away this pen and get a new one. All right, I do have a pen. Okay. Theorem 2.5 called Gronwall's inequality. Okay? Gronwall's inequality. All right. Let C be a non-negative real numbers. And let U, V be non-negative continuous functions on AB such that V of t less or equal to C plus A to 8, A to T, Vs, Us, ds. A less or equal to T less or equal to B. Then V of t less or equal to C e to the A to T Us ds. All right. True. Let C be positive and let H equal C plus A to T Vs Us ds. Then H prime of T is equal to Ut Vt, okay, which is less or equal to H of T Ut. Okay, so I am letting H equals C part as differentiate H. You will get Vt Ut, Ut Vt, but H is equal C plus A, and V, so H prime is U and V, and H equals C, but V is less or equal to H. So V is less or equal to H times Ut. Okay? So I have H prime of T minus H of T Ut equals 0. Okay? And then this one is dH over H of T equal to Ut. So that means ln of H of T is equal to A to T Us ds. Okay? Plus some constant C. All right? And so if I take exponential on both sides, I'll get H of T is equal to some K. Okay, let me make this as K. And let me make this as C. E to the AT US ds. Okay? So, but what do we know about Vt? Vt from here, Vt is less or equal to H of T, and so Vt is less or equal to C e to the AT US ds. And this is the proof. And for T between A and B. Of course, if C equals 0, then Vt is less or equal to 0 for all t. And this is if and only if V of t equal to 0, since V is bigger or equal to 0. All right. So this is what we call Grunwald's inequality. And it is a very powerful inequality. And people have done many variation of it. And it's very, very powerful. So let's go back to our theorem and prove the uniqueness of the solution. Okay. Okay. Back to our local existence theorem. To show uniqueness. Okay. Let yt be another solution. With yt naught equal x naught. So now we have x of t with x of t naught equal x naught. We have yt with yt naught equal x naught. Because if we have another solution that starts at the exact initial condition, then this is what we have. Then let w of t equal x of t minus y of t. Then w of t naught equal xt naught minus yt naught, that is x naught minus x naught, that is equal to 0. Moreover, w prime equal x prime of t minus y prime of t. Okay? If I integrate this, we get wt minus wt naught equal to xt minus yt. Okay? But what is xt? That implies w of t, remember this is 0, equal to x naught plus t naught to t f of s x of s ds minus y naught minus t naught to t f of s y of s ds. Actually, this is x naught too, so they cancel out. So that is t naught to t of f of s x of s minus f of s y of s ds. So take the absolute value is less or equal to t naught to t of f of s x of s minus f of s y of s ds. This is less or equal to k t naught to t of xs minus ys ds. Can anybody tell me why k xs minus ys? Anybody tell me, remind me why? Can you remind me? Remember the statement
Is
of
it
the two.
lip?
Yeah, go ahead.
Is it because it's Lipschitz? That was part of the. Okay.
Exactly. Because it's Lipschitz. Okay? So what do we have? So we have Wt is less or equal to K T0 to T Ws ds. Isn't it? Look. C is 0. So we're going to use, look what we have. Wt less or equal to K T naught to T Ws ds. Look, that is our V. C is 0 or plus. That is our U, and that is our V. So by Gronwall's inequality, W of t is less or equal to 0. This is if and only if Wt equals 0. This is if and only if Wt equals 0. This is if and only if xs minus xt minus yt. This is if and only if xt minus yt equals 0. This is if and only if xt equal yt. And the solution is unique. Beautiful. Okay? Any questions? What do you think? In the book, there is a typo. On page 39, I forgot to put C in. Okay? It's just a typo. All right. Any questions? Okay. So let me do another. Oh, I need to work on this. All right. Another application of Gronwall's inequality. So this is theorem 2.1.6. So suppose phi of t is continuous on 0 to infinity and differentiable on 0 to infinity. If the lim as t approaches infinity, phi of t equals zero, and 0 to infinity, phi prime of t dt is finite. Usually we make it like this, less than infinity. Then all solutions of x prime of t, x second of t, plus 1 plus phi of t, x of t equals 0 are bound. That's very powerful. But phi of t has to go to 0. The limit of it at infinity. Okay? So imagine the theorem. Okay? So here is the proof. We're gonna, this has a number. Let me give it to you. 2.119. Multiply 2.1.19 by x prime and integrate. So let me tell you. So this is x prime of t, x second of t, plus 1 plus phi of t, x of t, x prime of t equals 0. I have not integrated yet. This can be written as x prime of t over 2. No. X squared of t prime. Why? Because that will be 2xt times the derivative of, no, x prime of t. Let me see how I want to write it. Okay. I'm just trying to find the right way to write this. This is d of dt of x prime of t squared. There. How's that? And that is divided by 2. The x prime, this one, okay, so it is like this. Okay? Like this one. And then this is 1 plus phi t x of prime of t equals 0. Now we integrate. And integrate from 0 to t. Because t bigger or equal to 0. So if I integrate, what I get here is I get x prime of t over 2. No, I will get, yeah, x prime over t squared minus c1 plus the integral 0 to t, and that will be x of s, x prime of s, ds plus 0 to t, phi of s, x of s, x prime of s, ds equals 0. Okay? So what is the derivative of that? So this one, if you integrate this one, the integral of 0 to t xs x prime of s ds, like this one over there, is almost the same as 0 to t d of ds of x squared of s over 2 ds, and that is x squared of s over 2 from 0 to t, and that is x squared of t over 2 minus c2. Let me plus c2. So we have x prime of t squared over 2 minus c1 plus c2 plus x squared over 2 squared plus 0 to t phi s x of s x prime of s ds equals 0. So in the book, you can tell I skipped a lot of work. I still have not arrived. So this is what I have in the book, and then I waved my hand through some of it. So let's integrate phi s So we're going to integrate 0 to t phi s x of s x prime of s ds. We're going to do it integration by part. So we're going to let u equal phi and dv equal to x prime ds. So v is x squared over 2, and du is phi prime of s ds. We've already done this, how you integrate x prime. So this is equal to u v phi of s x squared of s over 2 from 0 to t minus v du minus 0 to t minus v times du minus x squared of s 2 phi prime of s ds. So this is phi of t x squared of t over 2 minus c3 minus 0t x squared over 2 of s phi prime of s ds. So this equation, the star, so star becomes I have x prime squared of t over 2 minus C1 plus C2 minus C3 plus x squared of t divided by 2. Okay, plus phi of t x squared of t divided by 2 minus 0 to t x squared of s phi prime of s over 2 ds equals 0. So let's call this one c. So I'll have 1/2 1 plus phi of t x squared of t, these two, plus x prime of t squared over 2 minus 0 to t phi prime of s x squared of s over 2 ds equals some number c. Okay, this is some number c. I don't know in the book what did I have it. Yeah. All right. So if I look at this, I'm gonna have 1/2 1 plus phi of t x squared of t is equal to minus x prime of t squared over 2 plus 0 to t phi prime of s x squared of s over 2 ds plus c, and this is less or equal to 0 to t phi prime of s x squared of s over 2 ds plus c. Can anybody tell me less or equal to? Because I have this minus something positive. Okay. All right. Okay, let's call double star. You see how much work I missed in the book. All right, because this is really heavy graduate texture. I was limited to the pages, so I skipped a lot of stuff. Now, since phi of t goes to 0 as t goes to infinity, there is a t naught bigger or equal to 0, so that for t bigger or equal to t naught, we have 1 plus phi of t is bigger or equal to 1/2, always. Okay? So thus, for t bigger or equal to 1/2, from star, 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 we get 1/2 x squared of t is less or equal to 1/2 1 plus phi of t x squared of t, and that is less or equal to 0 to t phi prime of s x squared of s over 2 ds plus c. You see what I have? Because of that. Okay? All right? Okay. So now multiply by 2. So we have x squared of t less or equal to c plus 0 to t phi prime of s, x squared of s ds. Wow. We are in a good shape now, finally. Okay. So let yt equal x squared of t. Then we have yt less or equal to c plus 0 to t phi prime of s, y of s ds. Then by Grunwald's inequality, we got y of t less or equal to c e to the 0 t phi prime of s ds, or x squared of t less or equal to c e to the 0 t phi prime of s ds. Guess what? What do we know about this? This is finite. Look at it. 0 to infinity. So this is less or equal to c e to the 0 to infinity phi prime of t dt. This is finite. This is less or equal to c times e to the number, to some number L, which is finite. So x squared of t is finite, mean x of t is finite. And then that proved the theorem. You see how elegant is? How eloquent? What do you think? All right. So this is really mathematics, good mathematics here. All right. Any questions? I'm gonna stop here. All right. Does anybody have any question? Let me see if there anything. No. Anybody have any questions? All right. I'll let you go. I'm gonna stop recording first.